Hey guys, welcome to another episode of Bob's Obscure Technology, Lore, and Arcane Curiosities, and I'm still working on a catchier title. You know, when I started making these videos, I did it for fun. I did not do it to be an educator, an instructor, a mentor, but during the course of some of these projects, I've had to do a lot of research, and I figure if I don't document it in some form, it's going to get lost. I hope some of you find it interesting, useful. At any rate, today's topic is going to be something that I myself did not understand very well, and I still don't completely grasp it. But I think I understand it better than I used to. And that is the way the whole horizontal deflection, circuit, damper, flyback, yoke stuff works. A lot of that I blame on the literature that I've read. So I've been asked in the past, how do I know what I know? From reading mostly. A little bit from experimenting, some from watching other YouTube videos, but mostly from reading. And I pulled out a bunch of literature. I went through about a dozen books and instructional guides and whatnot to kind of piece something together. And one online article. A gentleman whose name escapes me right now, I will certainly include a link to this excellent website. He went through and explained the history of the deflection, circuit, yoke, and damper from in the pre-war sets, before there was a damper tube. And that's where that's what got me rolling on this. But there were a few things I still didn't quite grasp until just a few days ago, where kind of a light bulb went off. I still don't understand everything perfectly, but there were a few key things that maybe they're obvious to all of you, but they weren't to me, so that's what we're going to talk about. As you can see, Jupiter is just dying to find out all about today's topic. And I get to play with some props. So this is an early cathode ray tube. Type 905. I pulled this out because it has no internal coating, so you can see what's going on inside. And this makes it really, really easy to understand how your basic cathode ray tube works. Heater, cathode, down at this end, produces electrons. Grid modulates it. High voltage anode at this end accelerates it towards the front. And there's a focusing element in there too that makes it into a tight beam. So, got an electron beam flying out from this end, phosphor at the other. If there was no deflection, we would just have a dot in the middle of the screen. That's it. To deflect it, I think it's pretty easy to see how they do that in this. We've got two sets of plates and 4 external connections. We've got a negatively charged beam of electrons going up. You put a negative charge on one side, it pushes them to the other side. Or if you have positive on one side, it pulls them that way. So by applying positive, negative voltages, you can make the beam go this way, and on the other set of plates, you make it go that way. Now you put a sawtooth on one side, a sawtooth on the other, synchronized. You can paint the electron beam over the face of the CRT. Really simple, really straightforward, makes perfect sense. So why didn't they just use this for all TVs? Why do they ever get involved with all this messy stuff with coils of wire and flybacks and damper tubes and all that stuff? Well, that's something I had no clue about. I knew these tended to be long, but they seem to work well, and there were some early TVs that used this electrostatic deflection. Why didn't they all? It turns out that not everything is created equally. Electrostatic deflection is not the same as magnetic deflection. For a given anode voltage acceleration, you need more voltage to deflect it than you do magnetic field. I forget what the exact mathematics is. I think for an electrostatic deflection it's like a square. In other words, if you were to double the anode voltage, you'd have to like quadruple the deflection plate voltage or make the CRT longer. Because if you don't deflect it as much but it's a lot longer, it's got more time to travel to deviate more. So that's one reason. And why would you want to have more anode voltage? Brighter picture. So electrostatic CRTs, early TVs, your 7-inch sets usually run like around 5,000 volts. Magnetic TVs tend to be more like 10 to 20,000 volts. So it's just not practical. There was one 10-inch electrostatically deflected CRT that was used in one or two models of TV. I've never seen one. I don't know the exact type of voltages involved, but it must not have been very practical because, well, they faded away from history. So that is why there is magnetic deflection. Now let's get into the particulars of how they do it. So magnetic deflection, basically you got two coils of wire around the neck of the CRT, one for the vertical deflection, one for the horizontal deflection. And you drive those with the vertical output tube and a horizontal output tube and transformers. Seems simple enough, right? And you use a sawtooth because you want to sweep it from left to right and from top to bottom, right? Okay, well, what's the big deal? Well, they are inductive loads. Inductive loads are a bit of a pain compared to resistive loads. I'll show you a real simple circuit I bet you a lot of you are familiar with. Say you want to drive an inductive load with an NPN transistor, like a relay or a solenoid. So say you got 12 volts, you've got your coil, collector on a transistor, emitter going to ground, and you got a control voltage here. You make this like positive 1 volt. Transistor turns on, saturates, you get current flow, the relay closes. What happens when you turn this off? Say ground this, transistor turns off, current stops flowing. But here's the thing. Inductors, similar to capacitors, store energy. You turn off the current, that thing is magnetized. It's got to go somewhere. The magnetic field starts collapsing, which induces voltage and current in the coil. It's got to go somewhere. Well, if you don't have this protection diode here, it fries the transistor. In other words, a large voltage is produced. It's got to go somewhere, and it's going to go in and zap the transistor. So you put this diode here to safely route it back into the B+. That's essentially what a damper tube is. It's a diode that when you're done sweeping the horizontal from one side to the other and you turn off the horizontal output tube, you got to snap that electron beam back to the other side. That collapsing magnetic field has got to go somewhere. So that's what the damper tube does, and that's why damper tubes are so rugged. They can take peak voltages of thousands of volts and a lot of current, and repeatedly, it's almost 16,000 times a second, getting hammered, so they can react very quickly, they can handle a lot of current, a lot of voltage, and they don't burn out. That's why it's a little bit tricky to replace them with just a simple diode. Okay, so what's the big deal? Well, it's not that simple. It could be that simple, and it was that simple in really early designs. So I pulled out a bunch of books here, and television servicing courses, and Sam's Photo Effect television course, and some Philco things, and some RCA stuff. And this book by good old Bernard Grob, who wrote some really good early television servicing stuff. So I'm going to just jump in and show you a few things that struck me as odd that I didn't realize at first. So you probably have seen the grid voltage going to the horizontal output tube, and it's typically a sawtooth. And in this version they're showing it like that, but more typically it's just a standard sawtooth wave. And you'd think, oh, okay. So when the sawtooth is at its lowest point, you're on the far left side of the screen, and as the sawtooth increases, you're increasing the magnetic field. It's moving the electron from the left side to the right side. It gets to the end, it snaps down, electron beam shoots back the other way, and you repeat. That is not the way it works. Just check this out. That is the plate current. The horizontal output tube is only conducting for about half of the horizontal period. Well, how can that be? If the tube is only conducting for about half of the screen travel from left to right, where the heck is the current coming from for the other half of the travel? Well, in modern, or relatively modern designs, it's coming from the damper circuit. That's the really clever thing. The damper is not there just to dissipate that energy with the collapsing magnetic field. No, what they actually do is they use it, they capture it in a controlled way and use it for the first half of the travel from the left side to the right side. So this is one of the things that was just escaped my brain. I wasn't thinking that, okay, if you just disconnected the horizontal yoke, where's the electron beam going to be? Where's that dot going to be? It's not going to be on the left side of the screen. It's going to be in the middle. So the way this actually works is when the horizontal output tube is conducting with that sawtooth, it's going from the middle of the screen to the right side. So everything from the side of the screen to the right is the horizontal output tube pumping energy into the yoke, essentially. When it gets to the end and the field collapses, that damper circuit provides the energy to get it going, to shoot it back to the left side and then bring it back to the middle. That is the magical thing. And early circuits didn't do that. I mean, they might even just use well, I'll show you some early schematics, but in the early circuits, the vertical and the horizontal are essentially the same. Think like a push-pull circuit driving a speaker. I mean, you also might be thinking, well, why is there no damper tube on the vertical output? It's got the same issues, right? Yes, and they could have. So, for example, here's a really early set. This is Dumont Clifton. I brought this out because it has a separate high voltage supply. There is no flyback transformer in this, per se. The high voltage is from a separate power supply. So here's the vertical. 6SN7, like a Class A amp, driving an output transformer. And then that goes to the vertical deflection coil. So it's just like driving a speaker. In, out, in, out. Electron beam up, down, up, down. Why is there no damper on this? Does it have a collapsing magnetic field? Yes, it does. But it's a much lower frequency, and there's a much longer blanking interval from the bottom of the screen back to the top. So the circuit can kind of have time to dissipate the energy and recover and so on. Higher the frequency you go, things get a little wackier. And this stuff does get hammered. You may see some like more modern sets than this. They'll have notes on here like "Don't measure this point," because there are some crazy voltage spikes when that electron beam snaps back. That just because it's lower frequency and they build a beefier circuit, they can just handle it without needing a damper tube, and they don't care about wasting the energy. For the horizontal, early sets, sometimes the damper would just be a resistor across the horizontal yoke windings, or it'd be an RC combo. But somebody got the bright idea of, hey, if we can capture that energy in a controlled manner, we can make this circuit a lot more efficient, and we can use a less robust flyback transformer and output transformer and so on. So check this out. This doesn't do that, really. So it uses two 807s in parallel. That's some serious power. And a horizontal deflection transformer, and driving the yoke. So it's very similar to the vertical deflection circuit, only it's a heck of a lot more power, because it's working at a much higher frequency. So this is 60 hertz, or this is 30 hertz. And this is almost 16 kilohertz. So it's got to be shooting that electron beam back and forth very quickly. And for the damper on this, it's not exactly a diode, it's actually a triode, a 6AS7 in parallel, which is a beefy triode that can take some abuse. And they have some variable controls on this to control damping and linearity. So some early sets, some early GE sets as well, use the 6AS7. And I don't think these really recover the energy so much as, well, I mean they do, and I shouldn't say that they do, otherwise it wouldn't be a linearity control here, but it's a little bit different action. It's a little bit less intense, I guess you could say. But at the expense of, they got to use much beefier power going into it, because I don't think this recovers the energy as efficiently as later designs do. And notice that there's no flyback, there's no winding going to a high voltage rectifier, and it's not producing the high voltage anode voltage for the CRT. Here's a different book that shows if you were to put an oscilloscope across the windings of the yoke, what you would actually see. So here's the vertical and here's the horizontal. Not exactly a sawtooth, is it? That's the weird thing. It's so if you instantaneously put a voltage across an inductor, the current cannot be instantaneous. There's a little bit of a lag. So putting basically a square wave onto a coil actually produces linear changing current. Something else maybe not so intuitive. Here's some other interesting waveforms. So here would be the sawtooth voltage on the grid of the horizontal output tube. But here's the actual current going through it. So this is what I meant by the horizontal output tube is not conducting for that whole ramp. It's only conducting for the second half. That first half, notice there's no current here. That's where the current for the first half, for the left side of the screen, comes from the damper. So when you see defects on the left side, like I had that bright vertical line or that ringing, that's all the damper circuit. Right side, horizontal output tube. Left side, damping. And here's some illustrations showing if you didn't have a damper tube, you get these crazy oscillations. Now there's something else about it that's curious. So these component values they use in the damper circuit, and the nature of the core material and so on. In particular, this stuff. So it was shown on a GE television recently. This is a very common setup where you have here's your damper tube, cathode, cap, coil, cap, and then into the flyback. This is set up to resonate not at 15.75 kilohertz. It's actually something like 4 times that frequency. Why? Because when it gets to the end of the screen, or when the electron beam gets to the end and the horizontal output tube cuts off, they actually do want that self-oscillation to happen for a brief bit, for that self-resonance, the huge spike. They want to let one big spike get through. Why? Because they want to use a huge chunk of energy to shoot the electron beam back to the other side and then damp it out. So it's like half of a cycle of the resonant frequency. And that's your horizontal retrace blanking interval. So they designed this stuff such that you get one brief pulse to shoot it back, and then you control it the rest of the way. Hope that makes some sense. That's I'm not 100% certain I have that fully grasped, but that's what I read in a number of these publications. And I thought this was curious too, because in that GE 800 they showed what the cathode voltage in the damper tube should look like, and that's what they showed in the service manual. It should look like this lumpy, weird thing. And when I had the defective combo flyback in there was like a huge spike, like right in the middle here, and that's where that really bright line was. And that I don't know. So all of my best guess as to why that doesn't work, because the flyback tests okay, is that there's something in particular I'm thinking with this stuff that's not copacetic with the flyback and the damper and these LC combos. So the natural resonant frequency of it is not correct. And we're getting some crazy spike in there. Some more servicing publications. This one is Tough Dog Sets. Now it's funny, these ones put out specifically by RCA or by Philco, of course, just pertain really to RCA TVs. But I think this one is the only instance I found where they talk about the problem we saw. So a lot of these manuals will show you examples of messed up TVs. So it's one cool thing about working on a TV is that once you've got something on the screen, it's a great troubleshooting aid. Just like in a radio, once you can hear something out of the speaker, it's a great troubleshooting aid. So even if you don't have a scope or a little fancy test pattern generator or whatever, you can see what's going on the screen, and by using these guides, it will help you figure out what the problem might be. And I believe they show a picture in here somewhere where it's got a bright vertical line. Well, they don't show exactly the issue that we saw, but there's some similar effects. For example, this with this horrible linearity on the left side, and there's basically a bright vertical line. Just a little hard to see it with the reproduction here. Or this type of problem. And this is curious, they just pulled the damper tube out entirely in this. So you can see without the damper tube, now with some designs you pull out the damper tube, you get nothing. But with this design, you pull out the damper tube, you only get the right side of the screen. That's the horizontal output tube doing its thing, but you don't have the damper circuit to do the left side of it. Or in this case, they messed with some of the component values and they got some vertical lines on the left. Some of these are kind of funny, like here they just put a permanent magnet speaker near the TV, and yes, of course, the magnetic field will mess with that magnetically deflected TV pretty badly. Now some of these are cool, like these Philcos, because this is really early publication, and basically all the circuits they refer to are the Philco 48-1000, which I now am very happy to own. So I can go through this lesson while I'm working on that TV. Just curious to see what the deflection circuit's like in this puppy. So they use a 5V4. That was another primitive type of damper tube. It's basically a regular power supply rectifier, but similarly such usage for a damper. There's two potentiometers for horizontal linearity and a coil, so I know this set's going to be a treat to work on because it's so, again, it's primitive. They hadn't quite worked all the kinks out, so I imagine it's going to be a little bit tricky to work on. This is a pretty solid book. I recommend. Television Servicing Course, put out by Beatman, 54. And here they talk about the screen image being messed up when the damping circuit fails, and you can see the left side, the linearity is just a disaster. Something somebody had mentioned that might be an issue with me, I said, is Barkhausen radiation. That's a pretty rare phenomena, but if you do see it, it shows up as kind of a thin, reedy line, I think they call it, or beady vertical line, and it's from like an internal oscillation happening inside the tube from some stray electrons. Very different from the kind of issue we're seeing with oscillation in the damper circuit. It's kind of annoying going through this. Really, none of these books show exactly the situation we encounter with that messed up flyback. With one really bright line and a few fainter lines. I think it's part of the problem. I had so much trouble with it is because it's not a common issue. I mean, if somebody puts the wrong substituted part in a set, it's not something that's typically going to be covered in service info. They're kind of assuming you're going to use the correct part. Alright, well, I hope this made some sense, and I don't doubt that I got some stuff a little bit wrong, so if any of you can help clarify any of these topics, I would greatly appreciate it, because it is a little tough to understand. Here's one of the better diagrams I've seen where they kind of show what's going on in all these different parts. So here they show the trace. Right trace, right retrace, left retrace, left trace. And there's the horizontal output tube. Sawtooth. So that's the thing, like you got a sawtooth on the grid, but the cutoff is in the middle of it. So remember, a tube doesn't start conducting until the grid is at a certain voltage. So actually half of that sawtooth, the tube is completely cut off. So again, that plate current is only on for that travel from point 1 to 2. And here's where it collapses and it quickly drops down. And here's the current through the deflection coil. So it's interesting, so from point 1 to 2, that is the horizontal output tube driving the horizontal yoke. And then point 2 to 3, and then 3 to 4 is where it's collapsing. And then 4 to 1 is, well, recovered energy from the collapsing magnetic field. So it's curious. Here's the voltage across the deflection coil. So from points 4 to 5, when the electron beam is actually traveling across the screen, there's no voltage on the coil. But there is across the linearity coil winding, and of course there's current going through it. There's voltage on the damper tube cathode. So, well, here's where they finally talk about that thing I was trying to find. That resonant frequency, so they're designed to have a resonant frequency of 70 kilocycles, which results in half a cycle of oscillation, so 7.5 microsecond for the horizontal retrace period. So that's that LC combination of the damper circuit. That's something I had no clue about, that there was a 70 kilohertz self-resonant frequency. I thought everything was centered around 15.75 kilohertz, you know, the horizontal oscillator frequency. Alright, I probably completely confused you. I hope some of that made some sense. I think that's going to be about it.